should we go ahead and get started?
Yeah, sure.
Yeah.
Hi, Martha.
Hi, everybody. Happy Friday. Happy Earth Day.
Yeah.
Does anyone have any announcements before we get started? I don't think I have any announcements.
Should have a dramatic one to start everything off.
I saw that the mentor-mentee connections have been made, so that was great to see. Moving that part of the program forward. So hope you enjoy, those of you who have a mentor now, a DOE. And just keep in touch, with any feedback that you have about how that's going. So today our presentation is from Stefani Kocevska. So Dr. Stefani. So Stefani is a PhD student at Georgia Tech who just defended her PhD thesis. So she's been working with us for 5 years, funded under CRESP. And so we thought now that she has defended and she's moving on to her next steps, that it would be good to have her give a presentation on her research to this group. So I think I'll just go ahead and turn it over to Stefani.
Great, thank you, Martha. Let me just share my slides. Can you see the screen?
Yes.
Or
Good.
are you seeing full screen, or because I have 2 monitors?
I only have a small screen.
Oh,
We're seeing the wrong one though. We're seeing the present
I
view.
see.
Yeah, we're
Okay.
not
Yeah,
seeing the presentation view. There you go.
Well, yeah, one more. Yeah.
Okay.
There we
And
go.
then hit F5 or share. There you go.
Hey, yay.
Alrighty, so let me begin. So my PhD was focused on looking at in situ monitoring and data-driven modeling for the nuclear waste systems at Hanford. And more particularly, I focused on liquid simulants throughout my PhD. So all of this research that I'm presenting today was related to the Hanford site. However, I do have some work that was done in collaboration with Savannah River that I will not be going over today. So as we all know here in this meeting, the Hanford site has approximately 55 million gallons of reprocessed nuclear and chemical waste that are stored in these tanks. So there's a total of 177 of them. Most of them are single-shelled, and there's some double-shelled tanks as well. So the real challenge with the Hanford site is the complexity of the waste. So there are all these elements shown in the periodic table, which means there's 25 chemical species as well as 46 radionuclides. And there's also the 3 phases in each tank. So as we go from the top to the bottom, we have less radioactivity, and then at the bottom is where the fission products are concentrated into the sludge. So there is, of course, an urgency to treat this waste, which unless it's treated, it could escape and it can reach containment and the Columbia River. And in some CRESP reports and the GAO report, they have shown that more than 1 million gallons of waste have already leaked. So the DOE has been in charge of coming up with a treatment plan. So the plan for the Hanford site waste is to remove all the waste from these aging underground tanks and immobilize the radioactive waste into glass. So this process is called vitrification, and it should keep the waste stable for thousands of years. So at the Hanford site, they're building the waste treatment facility plant that will be treating the waste, and the idea is shown here. So the overall plan is shown in the diagram here, but the plan is to pre-treat the waste and then have 2 streams. So to have a high-level stream as well as a low-activity radioactive waste stream. And even though both of them will be vitrified into glass, the storage would be different. So for the high-level waste, it would need to be stored in an off-site repository, whereas for the low-activity waste, it can be stored at the site. So while this waste treatment plant is being built, I will focus on the direct feed low activity waste, or DFLAW, which is scheduled to begin by 2023, and it will treat the low activity liquid waste at the site. So first, the waste will be pumped from the tank farm into the pretreatment facility, where the solids will be filtered out and the cesium will be removed with ion exchange. And then we get to this AP storage tank where the liquid low activity waste is stored. So from there, glass forming chemicals are added and the waste is being fed into the melter where the glass will form, and there's also a recycle feed for the effluents. So knowing the solution composition is really critical to calculate these glass forming chemicals so that stable glass can be made. And also the melter will be operating continuously, which means that it would be really good to have real-time information on this waste feed. So with this, this shows us that this complexity of the waste really calls for extensive sampling, and there is already plans for the Hanford site on how this sampling will be conducted. So for the low activity sampling, some of the analytes that are crucial for making stable glass and for measurements include molecular species such as the nitrate, nitrite, and sulfate shown here, as well as some of the cation species. And there's also a measurement of the radioactive elements that will be performed by other labs. So in this case, for example, for some of the analytes such as nitrate and nitrite, they need to be measured because they're really abundant in the waste. But when we look at the sulfate, it's not present in very high amounts, but it can interfere with the melter parts, so it also needs to be measured. And there's also a limit for how much sulfate can go into the melter. So all of these acceptance criteria need to be met and then formulated properly so that the glass can be stable. So some of the potential instruments that the DOE has proposed and evaluated for measurements of these analytes are shown here. So some of them include ion chromatography and inductively coupled plasma approaches. There's also LIBS, or laser-induced breakdown spectroscopy, that can look at the elemental analysis. And then there's also methods such as Raman and IR spectroscopy that can be used for real-time inline monitoring for the molecular species. And this is has been the focus on my PhD, looking into Raman and IR spectroscopy and checking how they perform for measuring some of these target species shown in the table. And the reason why we wanted to focus on real-time inline monitoring was so that the need for grab samples can be reduced, but also to enable online quality control and process control, like I mentioned previously. So when we reduce the need for grab samples, that means that we can have the information with the probes in real time, but also we're limiting the exposure to hazards for the employees that would be working with these grab samples. So the main focus of my work has been using two spectroscopy probes. The first one was Raman spectroscopy, which is a non-destructive technique that can measure the scattering of light by matter, which means that with Raman spectroscopy, we can pick up signals from both liquid and solid phases in a mixture. And in the bottom plot here, I'm showing some of the signals that we have been able to measure for these analytes that are found in the Hanford waste. So you can see that we do get strong signals for many of these species, but you also see some of the complexities that arise when you have a complicated mixture, since we have a lot of overlapping signals. So there's a challenge here in being able to accurately measure the target species, such as the nitrates or the nitrites and the sulfates that the DOE has evaluated as target species that are necessary for to be measured and for them to meet the acceptance criteria when the waste glass forming chemicals are added. The second probe that we were using is infrared spectroscopy. So we are using the ATR FTIR version, which is also a non-destructive spectroscopic technique. In this case, we measure the absorbance of the sample that comes in contact with this crystal. So with the ATR crystal, you only measure whatever can touch this ATR crystal. So the depth of penetration is very small, which means that we are only measuring the liquid portion of the waste, which could be beneficial if there's any solids present in this waste that would otherwise overlap or interfere with the Raman signal, but they would not do that for IR. So for the same species from this legend here, we can see their IR signals. And once again, you can see that we are able to measure these species, and we again see some overlap between them. So with this, I will go into the first part of the work I'm presenting today, which is developing a framework for real-time monitoring and quantifying these target species in the liquid waste. So when we have a well-defined system, meaning if we have only a few species that we want to measure and there are no additional species that we see at the Hanford site or no additional complications, this is the typical approach that we have. So with knowing the species that we want to work with, we go ahead and design a training data set. And then we measure these solutions with IR and Raman spectroscopy. So the training data set here will consist of the concentrations for these target species, as well as their spectroscopic signals. And this will help us build regression models where we can calculate the regression coefficients that relate these training concentrations with the signals. And from there, once we have the regression coefficients, we can apply these models to unknown mixtures, which would be the goal with Hanford, where we have inline measurements for unknown mixtures from the tanks. And from there, we can calculate the concentrations for these species on which the model was originally trained. So we went ahead and we designed the training data set, and the species that were included in the data set were the nitrate, nitrite, and sulfate, which were already identified by the DOE RTIM program. And we also incorporated carbonate. Just to remind you, the carbonate here is the purple species, and you can see that for both Raman and IR, it heavily overlaps with the nitrate. So we thought in order to accurately calculate the nitrate, we should also incorporate the carbonate. And the carbonate itself also has high concentrations in the waste. And then we used water as the solvent. So this was our simplified version of the liquid low activity waste at Hanford. And this is how we simulated it for this part of my work. So from there, we went ahead through the flow and we designed the training data set. So we used design of experiments to optimize how many experiments we need to collect, how many independent measurements, and we had a design with 36 measurements, and the levels for each component varied from low, medium to high. So you can see a representative spectra for both the Raman and IR here, and we have overlap again with the nitrate and carbonate, but you can also clearly see the sulfate and the nitrite. And you can do the same thing for the IR spectra. So we have the sulfate, nitrite, the overlapping nitrate and carbonate, as well as the water peak, which absorbs highly in IR and does not in Raman. So with this, we tested 4 regression models, which are commonly used in chemometrics. And the first 2 of them fell within the multiple linear regression category, where you go from your data set to the concentration space. And then the other 2 models fell into the principal component analysis space, where you first reduce your data set to get the variables that can maximize the variance in the data, and then you relate those to the concentrations. So typically there's an advantage in using data reduction techniques from the second category because they can lower the collinearity of these spectra. So from there, once we had the models defined, we went ahead and we measured the test data. So the test data consisted of 12 unknown mixtures that had the same species of interest. So this is representative spectra for both the Raman and the IR once again. And then we were able to calculate the concentrations for the target species. So I'm showing a parity plot here that has the measured concentration on the X and the model predicted concentrations on the Y. And you can see that for the Raman spectroscopy data, we were able to predict the concentrations of the target species well. And I'm showing here the plus and minus 20% prediction errors that are defined as the upper and lower limits by the Hanford Analytical Lab for their methods. And then if we zoom into the species individually, we can see once again that for all the species, we were able to get predictions within those bounds. So the next was to do the same exercise for the infrared spectroscopy data. And first, if we look at the left parity plot, we see that there is a greater spread in the predictions for the target species with IR. And in this case, the model was built by not including the water concentrations, which is typical since that's the solvent. But here we realized that the water absorbs highly in IR. So we went back and we incorporated the water as a species in this model. And you can see that that led to improvements in the predictions for the target species overall. And if we zoom in for this version of the model into the individual species, we can see once again that we were able to make predictions for all the species, and some of them are predicted well, such as the nitrate and nitrite. And then the carbonate and the sulfate are still predicted within the bounds, but there is more spread in the data. But overall, both models were able to predict well for the species for both IR and Raman. So the conclusions from this first part of my work was that we are able to use real-time Raman and IR spectroscopy to measure target anion species in simplified simulated ways. And we were able to show that multivariate linear models such as PLSR are able to predict these species concentrations from the signal. So this was just a proof of concept before I move into the second part of my work, where we increased the complexity of the data sets that I worked with. So in this case, we incorporated a blind source separation in addition to the PLS model from part 1, so that we can address more complex mixtures that have many species, so that are more representative of the Hanford side. So there's not only these 4 target species that I worked with in part 1, but there's other species that may not necessarily need to be measured, but they would still be present in the spectroscopy data. So some of those species include hydroxides, phosphate, acetate, oxalate, chromate, aluminate, and all of these species have a spectroscopic signal in IR and Raman. And it is important to note that for these species, they may have variable compositions in the diaflaw tanks. So in here, we have to ask the question, how we can train the models with all of these species. So here we have 2 options. Either we go ahead and build a big training data set for all of these species and all of their variations. So having high, medium, and low concentrations, which would take a lot of time, and it would be a very extensive study in the lab. And then if some of their compositions change and they're outside the training data set range, then we would not be able to quantify them accurately, and we would need to do some retraining of the models. So in this case, we had a question if we would be able to come up with some other way to pre-process the data to remove the signals of all of these non-target species and still be able to focus on the targets, nitrate, nitrite, sulfate, and carbonate, even in their presence. So to do this work, we went to source separation, which is an established technique, especially when we have signal mixing, such as music. So when you apply source separation algorithms to a mixture, such as a song, you're able to identify the sources. So what sources are producing that sound in the mixture. So we thought, let's apply this to spectroscopy data, where we have the mixture data X that have, this could be a mixture from diaflaw, so a measurement from one of the tanks. And we would like to use source separation to get the sources and the mixing coefficients. So in this case, the sources S would technically be the chemical species from the mixture data. So our nitrates, nitrites, and other species. And when we have this product of A and S, we would have the contribution of this source to the mixture X. So this would be a unique solution to that problem. So to apply blind source separation, we used two main algorithms, independent component analysis, as well as MCR ALS. And I can discuss these in more details, but the overarching goal was to be able to apply independent component analysis to solve for the sources, and then use that as a guess in MCR ALS so that we can iterate through and get a estimate for the sources in the end that was computed with this algorithm. So we applied these algorithms, and we made a framework in Python that would be automated, where you start with process data from the Hanford site, then you run the BSS algorithms, and you're able to match your sources that you get from BSS with a library of the target species. And then once you make a positive match, you can remove any species that are not in the target subset. And the final product from this framework is the prediction for the concentrations for the target species. So I will go step by step through this framework. And to start, we just worked with simulated IR spectra before testing this with real data. So in this case, we defined our target species subset, once again, with these 5 species: nitrate, carbonate, nitrite, sulfate, and water. And then to have a non-target subset, we used phosphate, acetate, and oxalate. So this was representative of some of the non-target species that can be found at the Hanford site. So then we applied the BSS algorithm, and it gave us 8 sources. This is the exercise shows the IR sources. So in the next few slides, we'll see the results by IR. But you can see in this case that we got 8 sources that should be the chemical species that are present in the mixtures. So then we went ahead and we classified the sources. So these sources that matched with the reference spectra for the targets were classified as the target sources. And you can see here how well they were matching with the references that we had on file. So in each of these cases where we were able to make a positive match for these target species. And then whatever was left was classified as non-target species, which meant that these sources did not correlate with the references for the target species. So we were able to confidently say that these sources belong to the non-target species, which was the acetate, phosphate, and oxalate. And from there, we subtracted any signal that belonged to the non-target species from our process data. And then this resulted in a pre-processed spectra that should only include the target species. So for example, you can see that in the region around 1000, where the phosphate should be, or it was in the beginning in the process data, it has now been removed, and we do not see any phosphate in the final data. And the goal here was, since we have removed any signals for these non-target species, then we can still use a simple training data set to calculate the concentrations for these targets. And we don't have to go to the lab and run a large calibration study that incorporates all of these additional species. So then we calculated these target concentrations, and you can see here, when we have incorporated the BSS pre-processing step in red, we get improved concentration predictions for the target species compared to just using a PLSR model that did not incorporate BSS into the work. So now that we showed that this can work for simulated data, we wanted to check how it works for real experimental data that were measured in the lab, where you have complexities such as matrix effects and any nonlinearities or other effects that can happen when you have a real experiment. So we have the training data set on the left that only have the target species. Then we have the test data on the right side that had both the target and the non-target species, and the goal was to be able to calculate the concentrations of these targets for the unknown mixtures. So without going through all the steps, you can see on the left side that the BSS algorithm was able to identify and subtract the signals of the non-target species. And then we were able to calculate the concentrations for both using a BSS pre-processing step with the model, as well as just using the model on its own. And you can see that once again, for the real experimental data, we were able to improve the predictions. Then we did the same thing for Raman spectroscopy data. So we have a training data set that had the same concentrations as the one with IR. And then we had the unknown mixtures which had the additional signals coming from the non-target species, in addition to the targets that you've seen in the previous part. So in this case, with the experimental data, we were able to once again make a positive match for the first 5 rows you see here for the target species. So we were able to identify the nitrate, carbonate, nitrite, sulfate, and water. However, in addition to that, we identified one species or source that did not correlate with only nitrate or only carbonate. It seemed to be a blue shift of the nitrate peak. And I will discuss this species in more details in part 3. However, for now, this did not go well with our BSS pre-processing because the automated framework identified this as a non-target source and subtracted it from the red spectra. So we were left with an underestimated nitrate peak. So to fix this, we went back and manually had to reclassify this source as a target species so that the nitrate concentration can be predicted accurately. But of course, this is not the goal of this framework since we want it to be automated. So this is why we did additional research to understand the behavior of this nitrate peak shifting and how it can be incorporated into the BSS framework. So once we had corrected the nitrate source or the nitrate shifting source, we were able to correct the pre-processing so that the nitrate peak was not underestimated, which led to improved predictions for all the target species when we used the BSS PLSR framework. So with this, I wanted to conclude part 2, where we were able to incorporate blind source separation as a pre-processing tool so that we can classify our species as either targets or non-targets. And then we're able to calculate the concentrations of the targets more efficiently. So this means that we do not need to incorporate any non-target or additional species into our modeling work. And if any of these species concentrations change in the tanks, that will not affect the model performance. However, we did come across this nitrate peak shifting phenomena, and we wanted to study that in more details and understand the extent of nonlinear behavior that occurs. So the blue peak shifting of nitrate happens at increased concentrations of the sodium nitrate in water, as you can see from the plot here. And this does not follow the linear Beer-Lambert law since you have a peak shifting in location. So to explain the behavior of the peak shifting, we turn to ion association theory, which describes the association of charged ions in electrolyte solutions. So at first we can have free solvated ions where you have a fully dissociated system. So you have the positive and the negative ions. However, as you increase the concentration in the system, you start getting solvent shared ion pairing, where the cation and the anion can share a solvation layer. Then if you keep going, you can start having contact ion pairs, where the ions start having direct contact, so there's no solvent between the cation and the anion. And finally, if the concentration is further increased, you may get complex ion aggregation or CIA, where even the contact ion pairs are associating, and there can be also association with free ions. So some of these behaviors can explain why we had peak shifting in the overall nitrate peak, since each of these behaviors, so for example, contact ion pairs, is associated with a specific subpeak in the nitrate peak. So we used a Gaussian fit in this data to deconvolute the nitrate peak. And you can see that as we start with a lower concentration of a sodium nitrate solution in water, where the solvent ion pairs are dominating the peak, once we increase the concentration significantly, we see that there has been a change in the subpeak ratios. So in this case, the CIP, or the contact ion pairing, is the one dominating the peak of nitrate, which has resulted in overall shifting this peak to the right side. And we can also see that we have complex ion aggregation appearing, which was not present at lower concentrations. So that was really interesting to see that by changing the concentration of sodium nitrate, we can alter the peak of the nitrate itself. So then we wanted to see how this behavior happens when you have binary solutions. And we looked at the sodium nitrate in water as the reference, shown in red. And then we started adding salts. So we had sodium nitrite, carbonate, sulfate, and phosphate. And we chose these because they're present in the Hanford waste. So we wanted this study to be relevant for the diaflow liquid mixtures that we worked with. And you can see here, as we increase the ionic strength, the concentration of anions and the concentration of cations in the solution, we have the peak shifting that is increasing. So on the right, on the axis here, the vertical axis, you have the wave number for the center of the peak. And you can see that when we use, for example, ionic strength, we can't really have a predictor. So at the same ionic strength, let's say of 6, you see different amount of peak shifting. But if we look at the cation concentrations, we see that the behavior seems to be better predicted. So when we look at the cation concentration of 6, all of the solutions behave similarly and have a similar extent of peak shifting. Then we looked at the subpeaks themselves. So we looked at the fraction of each subpeak area. And you can see that as we are increasing the concentration of the cations, we see a decrease in the solvated ions. And then we see an increase in the contact ion pairing, as well as the complex ion aggregation happening as you're increasing your concentration, which made sense since that leads to peak shifting. And then we also wanted to check the extent of peak shifting that happens in Hanford samples. So for this, we used the nitrate system again as a reference, but then we also used the training and the test data from our previous work, as well as the blue samples, which represent diaflow simulated waste that was sent to us by Savannah River National Lab. And it incorporated all the target and non-target species present in the waste. And we can see that even in this case, we are seeing peak shifting. So this peak shifting behavior is present in all of the Hanford simulated waste for diaflow. So with this, I wanted to conclude part 3. So we showed that there is a blue shift in the Raman nitrate peak, and it's caused by ion coupling in these salt solutions. And it seemed that the cation concentration is a good predictor for this peak shifting behavior in binary systems. And we also showed that this is present in spectra of the liquid diaflow simulants. So this would be important to incorporate in any future models so that this nonlinear behavior can be estimated and incorporated in, for example, the blind source separation algorithm that we are using, for example, by incorporating these subpeaks as separate sources instead of only having one source for the nitrate peak itself. So to summarize my work that I presented today, in part 1, I showed a proof of concept for using IR and Raman spectroscopy for a real-time monitoring of nuclear waste with a special focus on the target species that are molecular and need to be measured in real time. In the second part, I showed the use of blind source separation so that we can classify the contributions of the target species and quantify their concentrations in more complex systems where you have presence of many other additional species that may not necessarily need to be measured for making a stable glass form. And then in the final part, we further explored the presence of nonlinear phenomena in our systems that were related to ion coupling in the salt solutions. And this was having an effect of the nitrate peak on the nitrate peak in Raman spectroscopy, which has an effect on our modeling and whether the system is linear or not. So some of the future directions of this work can include evaluating the applicability of IR and Raman for slurry samples. So while in this work, I focused on the liquid portion of DF law, once you go towards a GFC addition or adding the glass forming chemicals, you're forming a slurry and this sample also needs to be measured. So in this case, IR could be beneficial since it only measures the liquid portion of the waste. And then related to part 3 of this work, we need to understand the limitations of the linear models in presence of nonlinear phenomena. And also there should be work using these applications for the Savannah River site, where they also want to incorporate an ATR FTIR probe to study the slurry samples that they have in their defense waste processing facility. So there's a lot of future work that may be interesting to explore related to this project. So with this, I wanted to acknowledge my advisors, Drs. Martha Grover and Dr. Ron Rousseau, as well as everyone who has worked on the nuclear team, and Rupanjali and Stephen, who are present here and will continue working on their CRESP. I also wanted to thank our collaborators and funding. Thank you. I am open to any questions.
I have a couple of questions,
Sure.
starting with a real simple one. How sensitive is the treatment process to variations in the results you give them? And is this so sensitive that a tiny deviation in one of the prediction equations could cause the system to get gummed up? Or are you doing this carefully and precisely because you're trained to be a good scientist and want to turn out good science? I guess I'm trying to look at it wearing my policy hat versus my science hat.
Yeah, that's a very good question. And I also wonder, I mean, we know the acceptance criteria from these reports, but in the end, I'm not sure how much that affects the formulation of the glass. I think Kevin might have a raised hand.
Yeah, having done this before, Mike, at Savannah River, what they do is they incorporate the expected uncertainties into the predictions themselves to account for those when you actually try to process the waste. So, for example, you'd add more or less of a glass forming chemical based upon the prediction of what's coming through the process. So it's accounted for that way.
So in other words, if you wanted to be extra special careful, you could run a model and then allow for variations using some kind of Monte Carlo variations. And you're saying that's already incorporated into it?
Yeah, you have to, for high level waste glass. Now this is a low activity, but they tend to control it the same way. What you do is you control it to a defined confidence level. So what we did is we went through, and John Vienna is the one who does this at PNNL, so they do a very similar thing, and the statisticians. So we did a tremendous amount of testing before we started up DOPF. They're doing the same thing. So you have estimates, multivariate estimates of the uncertainties going through these things, and you incorporate those into your predictions. So you back away accounting for the uncertainty that you're talking about, how you add the glass forming chemicals to make the glass in the first place.
And Kevin mentioned John Vienna, so I know he's done extensive studies with sulfur. So I think it also depends on the species you want to measure. So for some of them, it's more sensitive because I think sulfur can corrode some of the melter elements. Well, so actually, they want to really limit that.
Yeah, so sulfur actually makes a non-conductive layer. And when you're running a Joule heated melter and you form a non-conductive layer in your conductive layer, I'm sorry, it actually shorts out your melter. And it forms as a scum layer on the top that in the commercial industry, they just skim it off. You can't do that in a high level waste melter or a low activity waste melter. So things like that, or things that can plate out, Mike, due to redox and other effects that go across the bottom and form conductive layers. Things like sulfate, the halides. There are certain things that will degrade the electrodes and the refractory. So all these limits that you see are based upon those. Or if the glass is too viscous or not viscous enough, or if the crystallinity of the glass is such that these things start falling out in the glass itself, we control over all these properties. So it's a very, we live in 30-dimensional space. Stefani mentioned 46 and 26. Actually, these glasses have the periodic table in them. It's just most of them you can't measure at those levels. So they keep track of 46 and 46 rad or 46 chem and 26 rad, because that's what they can measure in the other way around. That's what they can measure in the tanks. But a lot of those don't contribute to the properties that we worry about screwing up a melter.
So I have to tell you, because a lot of the data I use, of course, is social science data, and I'm looking at some of those models you had that you were suggesting were not too precise. They look a heck of a lot better than what I get with the data I use. But of course, that's when you have human beings involved, that anything could get messed up.
Well, and you asked another really good question. What we do at Savannah River is we take actual waste and we do a variability study with that actual waste, and we make glass out of the actual waste based upon what we think how it's gonna vary through what's called the sodium evaporator, actually going into the glass, the melter itself. So we do a variability study offline before we even run it through a melter. So we do a lot of work to make sure it's going to make acceptable glass before we ever run it through a melter.
Okay, I mean, so I have two other points. One is, now that I see what you did, if you want to, I could still walk through the canonical correlation method with you. And the difference
thanks for the reminder.
between PCA and the regression models is the math underneath canonical correlation. The second set is optimized to fit the first set. So I see that you used PCA, but the model that you get from the independent variables is not optimized into the ones you're trying to predict, where canonical is made for that. So I mean, I think it's worth trying. I don't know that it'll make any difference, but it'd be fun for you to see if you could use it.
Yeah, I think canonical is similar to one of the models I have, PLSR, where you look at the covariance between the independent and the dependent variable. So I know you don't do that with PCA, but you do it with PLS.
Yeah.
But it would be interesting to compare,
Okay, so when you have time, give me a buzz.
So Mike, let me ask you a question about that.
Yeah.
The issues that we always had, because like I said, we used to work in 30-dimensional space. So we tried PCA, but we would always come up with principal components that had no significance from a physical or phenomenological standpoint. So I have a lot of trouble using things like that. Does that get you closer to something meaningful when you start looking at PCA? Principal components?
You have to really understand the theory. So if you get some result that even if it's statistically significant, you can't explain through theory, either one possibility is you just discovered something worth investigating, or it's just some statistical nonsense.
We were tracking noise is what I think we were doing, to be honest.
But again, in the data I use, you can get a lot of unexplained stuff with PCA, and once in a while it actually turns out to be real, but you hadn't thought about it ahead of time. So
these are compositions and things, so typically you don't have that sort of effect running around your data. Yeah, but I was just curious. Thank you.
Yeah, now see what with canonical works really well when you have two data sets which you think are conceptually related through theory. I mean, it all starts out with the theory. If you put crap in with crap, you're going to get crap. But if you have two things that should be related, canonical will say, well, how do I fit this data set most effectively into this first data set? And that's what it's mostly been effective at doing. So it's worth a try.
Kevin, you might want to try independent component analysis, ICA.
So back in the day, sorry, go ahead. Go ahead.
No, go ahead.
You know, back in the day, there were two of us trying to do this in 30-dimensional space and the people trying to model the stock market. We were much more successful than they were.
I'll bet.
I'll leave it at that. But I'm sure things have changed since then. We do a little bit different. We ended up a little bit differently than that in terms of how we modeled these systems, because the PNNL people work very differently. They tend to throw Chaffee and highly dimensional. They like to soak up variance, Mike.
Mhm.
They don't worry so much about the parameters soaking up the variance having physical meaning. We kind of have less variance soaked up, but all of our parameters tend to make sense fundamentally or mechanistically. So there's a very different mindset at the Savannah River site than there is at PNNL for Hanford.
Okay, I mean, I think in social science, it becomes a daunting challenge to keep people from running these advanced statistical tools, coming up with results, and then after the fact, fitting some theory to it. Whereas I think in your case, there is some logic in physics and chemistry that works. That if you find something crazy, you're going to look at it and say, wait a minute, this doesn't make any sense.
So in 30-dimensional space, it's very easy to get outside that domain because it's a very complicated space and it's very difficult to prove that you're in the right domain. So you're almost always extrapolating if you don't have some sort of mechanistic basis for the parameters in your model. And that's something we've been fighting about for 30 years now. So it's an interesting thing, the track noise versus actually have less variance accounted for, but better parameters in the model.
Yeah. Well, that's very interesting. I'm glad to learn what you're doing now. So you let me know if you want to.
Well, I leave it to young people now. I don't do any real work now. You know that. Not statistically speaking.
If you're old, then what am I? See, Craig is enjoying all this.
He's just happy I didn't ask him a question about uncertainty this time. That's all it is. So.
I heard, Kevin, that you're not working on anything, so I got to talk to David, see if we can get you some more to do.
Yeah, we were just talking about that earlier, and we'll be again in a few minutes.
I'm wondering if we have any questions from the early career folks.
Good idea, Martha.
And the chat is also fine, or just ask Stefani.
See, I like to ask questions, Martha. You get me in one of these. You fill up all the time.
Does anyone non-early career have another question? Well, thank you all. It was good to see you all. And thanks to Stefani for sharing her graduate work with us, and congratulations.
Great talk.
Yeah.
To Stefani. So we'll meet, the committee will meet next week, and then the whole group will meet in 2 weeks.
I got a question, Martha. What's Stefani doing next? Stephanie, what are you doing next after you finish your PhD? Maybe I missed it.
So I'll be working in process development at Gilead.
Great, good for you.
Thank you.
Good question. All right, thanks everyone. Have a good weekend.
Bye-bye. Enjoyed it.
Thanks.